Usually when we talk about precision, there's this expectation of a highly controlled, almost delicate environment. Like we picture a watchmaker in this completely silent room
Right.
using tiny tweezers. Or, a surgeon with a microscopic scalpel. It's clean, it's quiet, and it's highly, highly predictable.
Yeah, we definitely tend to associate high accuracy with fragility.
Yeah.
The underlying assumption is that to be perfectly precise, you must eliminate all external forces.
That's exactly.
Like you have to create this sterile vacuum where literally nothing unexpected happens.
But today, we are looking at some really fascinating engineering research to figure out how you maintain that kind of microscopic perfection inside a machine that is quite literally violently ripping apart solid steel.
It's intense.
It is. We are doing a deep dive into the design of the sleeve-type spindle in a CNC turn mill center. And our mission today is to unpack how manufacturing engineers solve what feels like a completely impossible physics problem, which is, maintaining absolute geometric perfection inside this high-heat, high-impact kinetic war zone.
And, the way they approach this problem goes way beyond just heavy machinery.
Yeah.
It really offers a masterclass in resilient system design.
Okay, let's unpack this because we need to start with the environment itself, just to understand the stakes. A CNC turn mill center is not just some fancy drill press sitting in a guy's garage.
No, not at all.
This is a massive industrial machine, and it combines multiple manufacturing processes into one enclosed space. So you have turning, which is essentially a lathe, right? You're spinning this heavy chunk of metal at thousands of rotations per minute.
Thousands, yeah.
While a stationary blade basically peels off layers.
And at the exact same time, or at least in the exact same setup, you have milling. And milling is kind of the opposite.
Right.
The metal stays still, or maybe it rotates really slowly, while a spinning blade plunges into it to carve out flat surfaces or pockets or these really complex contours.
So doing both of those things in the exact same machine means you have, coolant spraying everywhere at super high pressure,
Right.
heavy metal chips flying around, and all these varying acoustic frequencies just bouncing around the chassis. The speed and the load are constantly changing. I mean, it is an absolute nightmare for stability.
It really is.
Yeah.
Which introduces the foundational subject of our research today. To actually survive that environment, engineers utilize what's called a sleeve-type spindle. Sometimes you'll hear it referred to in the industry as a quill-type spindle.
Okay.
Now, the spindle is the main rotating shaft of the machine. It's the core component that's actually holding the workpiece or the cutting tool.
Right, the heart of the machine.
Exactly.
Yeah.
But instead of bolting the spindle and its really intricate bearing system directly to the cast iron frame of the machine, piece by piece, this design encases the entire assembly inside a highly rigid, perfectly cylindrical metal sleeve.
So it basically creates a protective microenvironment. The delicate spinning core of the machine is isolated within its own dedicated armor, rather than just being subjected to the unpredictable structural shifts of the whole larger machine frame.
That isolation is key. By placing the spindle inside this pre-assembled sleeve, engineers can create a highly controlled mechanical and thermal base, long before it ever gets installed on the factory floor.
Because before the machine even turns on, and before the metal starts flying everywhere, you have to establish perfect geometry. The baseline question here is how you guarantee a cutting tool will hit the exact same microscopic mark every single time.
Right, because everything in machining begins and ends with alignment. The research really emphasizes that even the most minuscule alignment errors between the front and rear spindle bearings create a condition that engineers call runout.
Runout.
Yeah, runout is basically, it's a wobble.
Ah, okay.
When a spindle shaft rotates, it should spin perfectly on its center axis. If it wobbles even a fraction of a millimeter off that axis, the consequences are severe.
And I guess a fraction of a millimeter might not sound like much to the average person, but if you are machining, say, a titanium component for an aerospace turbine, that tiny wobble means the surface finish is completely ruined.
Apparently.
The part fails inspection, and because the cutting tool is just vibrating against the metal instead of slicing cleanly through it, the tool shatters prematurely.
Exactly.
Yeah.
So to prevent that wobble, the sleeve design establishes what they call a common positioning datum.
Okay, a datum.
Yeah. In manufacturing, a datum is just a unified reference point. In a conventional, older machine setup, the bore for the front bearing might be machined into one part of the main casting, and the bore for the rear bearing might be machined into another, entirely different part.
Oh, wow.
So you are relying on the overall machine frame to keep those two separate points perfectly aligned.
I love this concept, actually, because it immediately makes me think of building a house.
Oh, yeah.
Yeah, so imagine you're trying to hang a pair of heavy French doors so they meet perfectly in the middle.
Okay, sure.
But you are hanging them on two completely separate walls that were framed by different people at totally different times.
Oh, man.
Right, you would be constantly adjusting the hinges, adding shims, and just fighting the geometry to make these two different reference points agree with each other.
And over time, as the building's foundation settles, or even if the wood just expands from humidity, those two walls are going to shift independently, right?
Exactly.
Which throws your doors out of alignment all over again.
Yes, so using a common datum is like throwing away those two separate walls entirely. Instead, you hang both doors on one prefabricated, incredibly rigid steel frame.
I see.
Everything references that single perfect frame. There's no guessing, and there is no independent shifting.
That's a great way to put it. Because the sleeve design forces the front and back bearings to share the exact same physical cylinder, the assembly dramatically limits those accumulated errors.
Right.
The spindle shaft basically has no choice but to rotate around a perfectly stable center line. And what's fascinating here is that this stable rotational datum becomes incredibly powerful when it's paired with advanced electronics,
Okay.
specifically a high-resolution encoder for the C-axis.
Wait, C-axis, I'm familiar with like the X, Y, and Z axis for moving up, down, left, and right. How does the C-axis fit into this?
So the C-axis controls the rotational position of the spindle itself.
Oh, I see.
In a turn mill center, the spindle doesn't just spin continuously at high speeds like a standard lathe. Sometimes it needs to act like an indexer.
Like it has to stop.
Right. It has to rotate a piece of metal to a very specific angle, stop, and hold perfectly rigid so a separate milling tool can drill a hole off to the side, for example.
Okay.
The high-resolution encoder is essentially this hyper-accurate digital protractor that's reading that rotation. And when you combine the geometric perfection of the sleeve with that digital feedback, high-end systems can achieve angular positioning and repeatability of up to plus or minus 1 arc second.
Okay, I actually had to look up the math on an arc second before we started because the scale of that is almost unfathomable to me.
It's tiny.
It is. An arc second is 1/3600th of a single degree.
Yeah.
Being able to rotate a massive steel shaft, stop on a dime, and reliably hit a mark that is a fraction of a degree, I mean, that requires zero play in the system.
Zero play. But to reliably hit that mark while under physical stress, the design also relies on a physical concept called short overhang.
Short overhang.
Right. Even with perfect internal bearings, the cutting tool, or the part being machined, needs to sit as close to the front bearing support as physically possible.
That makes total sense when you think about leverage. Like
Right.
in physics, that distance is called a moment arm.
Exactly.
So if you hold a heavy bag of groceries straight out in front of you with your arms locked, it feels incredibly heavy, right? And your arms start shaking
Oh yeah, you can't hold it for long.
because the moment arm is long. But if you pull that grocery bag tight against your chest, it's so much easier to hold stable. The sleeve design basically reduces the moment arm, so when the tool is pushing hard against a piece of steel, the nose of the spindle doesn't bend.
And that reduction in bending brings up the core challenge of the actual machining process, honestly, because geometric perfection at rest in a nice climate-controlled assembly room is relatively easy to achieve.
Sure.
Metal cutting, however, is a profoundly chaotic process.
Yeah, geometric perfection is entirely useless if the machine just shakes itself apart during a cut. The kinetic energy we were talking about here is extreme.
It is.
You have situations like interrupted cuts, where a tool is turning a piece of metal that isn't a perfect cylinder, so the blade is cutting solid steel, then hitting an air gap, then violently slamming back into the solid steel over and over again.
It's incredibly jarring.
Or you have off-center milling, which sends these huge lateral shock waves right through the machine.
And the sleeve-type spindle survives that kinetic energy through load distribution. It doesn't attempt to absorb all that violence internally. Instead, it relies on peripheral support.
Peripheral support.
Yeah, the outer wall of that cylindrical sleeve is designed to fit incredibly closely inside the main, really heavy cast iron housing of the machine.
So the sleeve is making full wraparound contact with the casting.
Exactly. Rather than bolting a traditional spindle unit to the machine frame using just, 4 bolts in the corners,
Yeah.
the forces from the cutting process pass directly through the rigid outer wall of the sleeve and dissipate into the massive bulk of the machine structure.
Wow.
The path the energy takes is short and highly rigid.
It goes back to a weightlifter analogy, I think. If you want to hold a heavy barbell steady, you don't stand on one foot and hold the weight away from your body.
Right.
You take a wide, solid stance to channel the weight through your skeleton and directly into the floor. The peripheral support against the machine frame acts as that wide, solid stance.
That's a perfect way to visualize it.
It channels the chaotic vibrations away from those delicate internal bearings and bleeds that energy into the heavy cast iron.
And the cylindrical shape is specifically chosen because those chaotic forces are so unpredictable.
Right. They come from everywhere.
Yeah, heavy turning creates a steady, continuous force from one side. But off-center milling changes direction constantly as the tool moves. Deep drilling creates axial thrust, which literally tries to push the spindle straight backward.
Oh, wow.
A cylinder handles forces from 360 degrees equally well, so it just shuts down the amplitude of those vibrations regardless of where they originate.
And the engineers also look for internal variables to eliminate, right? Like if you can stop vibrations from being generated inside the machine, you don't have to fight them as hard on the outside.
Precisely. And that is where the integration of direct drive motors comes in. Traditional spindle setups often use an external motor that's connected to the spindle shaft by this whole series of belts or pulleys or gear couplings. But high-end sleeve spindles embed the motor directly into the sleeve itself, physically wrapped around the shaft.
Because belts and gears are just extra parts that stretch, wear out, or, introduce slack, right?
Yes. In mechanical engineering, we call that slack backlash.
Backlash.
Yeah, backlash is the tiny, sometimes microscopic gap between moving parts. So if you have a gear driving another gear, there's a tiny space between the teeth.
Okay.
When the motor changes direction or encounters a sudden spike in resistance from the cut, that gap closes violently.
Like a slam.
Exactly. It creates a microslam, which is a tiny vibration that echoes right down the shaft and manifests as a chatter mark on your beautiful aerospace part.
Ouch.
But by utilizing a direct drive motor, you eliminate belts, gears, and couplings entirely. You remove backlash in the transmission chain, leaving a vastly more stable cutting process.
Okay, so we have conquered the initial geometry, and we've figured out how to survive the physical impact and the mechanical vibration. But as I read through the research, I realized there is this completely silent killer of precision lurking in the background.
Oh, yeah.
Thermodynamics. Heat.
Heat is the fundamental enemy of all metalwork. The friction of the cutting tool tearing through steel, combined with the high-speed rotation of the bearings and the electrical energy of the motor itself, it generates massive amounts of thermal energy.
And heat causes metal to expand. But I actually want to push back on this a little bit because this is where my intuition clashes with the engineering.
Okay, let's hear it.
If the entire inside of this machine is getting hot from the cutting process and the motor, why are we fighting nature? Like, why not just let the metal expand? As long as everything expands together inside the machine, why does it matter?
This raises an important question, and it's a very logical one. The answer comes down to two specific realities of physics: internal bearing preload and asymmetrical thermal expansion. Let's look at the bearings first.
Here.
Spindle bearings are not just casually dropped into their seats.
Right.
They are installed with a highly calculated mechanical tension called preload.
So they are actively squeezed into place to keep everything perfectly centered.
Exactly. They are packed tightly together, often using steel balls or ceramic rollers that are compressed between the inner and outer rings. There is zero wiggle room. So when uncontrolled heat floods the system, the different metal components do not expand at the exact same rate.
Oh.
The rotating inner shaft might heat up much faster than the outer housing, for instance.
Oh, I see. So if the inner ring expands outward faster than the outer housing expands, it basically crushes the ball bearings trapped in the middle.
Yes. Too much heat alters the internal clearance. It creates excessive preload. The bearings are suddenly grinding against their tracks. And that friction creates even more heat, which creates more expansion, leading to a runaway thermal event where the bearings literally destroy themselves in minutes.
Oh, wow, in minutes.
Yeah, and conversely, if the outer housing heats up and expands away from the bearings, you lose your preload entirely. Suddenly your spindle is loose, and you've introduced runout back into the system.
So you really cannot just let the heat run wild because it fundamentally alters the physical mechanical tension that's holding the whole system together.
Exactly. And the second issue with letting metal expand naturally is that traditional machine structures are not uniform. A standard cast iron headstock might have a really thick wall of metal on the left side for structural support and a much thinner wall on the right side just to make room for a tool changer.
And thick metal and thin metal will heat up and expand at completely different speeds.
Exactly. The heat distributes unevenly, causing the metal to warp. The thicker side pulls the entire structure, literally dragging the spindle axis off-center.
That's crazy.
And this is where the geometric genius of the sleeve's symmetrical construction really shines. Because the sleeve is a perfect cylinder, its mass is distributed equally around the rotational axis.
Oh, so when a perfect cylinder heats up, it expands completely evenly, like a balloon inflating.
Yes.
It doesn't warp to the left or the right, it just grows outward uniformly in all directions.
That rotational symmetry uses pure geometry to outsmart thermodynamics. The structure might get larger on a microscopic scale, but the center point remains perfectly stationary. That dramatically reduces radial center drift during a long, heavy machining cycle.
But they don't just rely on the shape to passively handle the heat, right? The research outlines a highly active defense mechanism, which is wraparound cooling.
Right. The engineers actually machine internal cooling passages directly into the sleeve structure itself.
Wow.
These channels spiral around the spindle and the bearing seats. The machine constantly pumps a controlled liquid, usually water or a specialized coolant oil, through these passages to absorb the heat at the exact source of generation, pulling it out of the machine before it can soak into the larger cast iron frame.
And one detail in the document really stood out to me here. They use entirely independent cooling circuits. Like, the motor has its own dedicated liquid cooling loop, and the front and rear bearings have theirs.
That's crucial. A built-in electrical motor and a set of mechanical friction bearings generate heat at entirely different rates and peak temperatures. The motor might safely run much, much hotter than the delicate front bearings can handle.
So if they shared the same plumbing line, you might be taking boiling hot liquid from the motor jacket and pumping it directly over your front bearings.
Exactly.
You wouldn't be cooling them, you'd basically be cooking them.
By isolating those circuits, the system maintains discrete thermal zones. The motor gets the aggressive cooling it needs, while the front bearings are kept at a precise, stable temperature to maintain that critical preload tension we discussed earlier. It prevents local hotspots from ever forming.
Okay, so we have this absolute marvel of engineering. It is a geometrically perfect, shock-absorbing, thermally balanced, liquid-cooled cylinder. It's beautiful.
It really is. But let's step off the pristine drawing board and onto the actual messy factory floor for a minute, because physics is only half the battle, right?
Oh, definitely.
Eventually, components wear out. Operators make mistakes and crash the cutting tool into the chuck. Things break. What actually happens when this highly complex machine needs repair?
This is where the design philosophy shifts from physics to economics. In a conventional spindle design, an overhaul is a catastrophic event for a production schedule.
Really?
Yeah, it requires a massive teardown of the machine's headstock. You are draining fluids, removing belts, and pulling components apart piece by piece.
It sounds like having to take the entire engine block out of a car just to fix a single stretch timing belt.
It is exactly like that. The labor requires a highly specialized technician. You face days, if not weeks, of production downtime. And once the new bearings are finally installed, the technician has to painstakingly realign the spindle with the machine's axes using laser trackers before you can cut a single part. And the sleeve-type spindle approaches this entirely differently, right? Through modular replacement.
Yes.
The entire sleeve, like the bearings, the seals, the internal cooling channels, and the spindle shaft itself, is engineered as one independent quill assembly. It essentially functions like a cartridge.
That's the brilliance of it. If a bearing is destroyed in a crash, the maintenance team does not dismantle the heavy machinery. They disconnect the cooling lines, unbolt the flange, pull the damaged cylindrical module straight out of the machine housing, and slide a newly rebuilt, pre-aligned module right back into the same hole.
That is amazing. And the economic impact of this modularity is just staggering. The research indicates that utilizing a cartridge-style sleeve can shorten maintenance downtime by more than 60%.
And 60% reduction in downtime is a massive competitive advantage.
Huge.
Because every single hour a CNC machine sits idle, the factory is losing money. Furthermore, the economic benefits begin long before a crash even occurs. That independent wraparound cooling system we discussed, it keeps the internal temperatures stable. Stable temperatures protect the viscosity of the bearing grease from breaking down.
Oh, and keeping the grease healthy reduces the rate of bearing wear by 30 to 50% from the start.
Exactly.
So the machine lasts up to 50% longer, and when it finally does break, it takes 60% less time to fix.
It's a win-win.
The document also points out that the modular approach lowers the cost of spare parts. Because the sleeve uses standardized dimensional interfaces, machine owners can keep a spare cartridge just sitting on the shelf or source one quickly rather than waiting, 6 months for a custom-built component to ship from the original manufacturer.
And it democratizes the maintenance process. Trained plant technicians can often swap the sleeve themselves after just basic instruction.
Yeah.
They don't need to fly in a senior spindle specialist just to get the production line moving again.
So what does this all mean? When I was looking over the economic data, it struck me that this isn't just about cutting metal efficiently. This feels deeply connected to the right to repair philosophy we see debated in consumer tech all the time.
That's an interesting connection.
Yeah, by standardizing the interfaces and creating these quick-release modular structures, the engineers are designing the machine to respect the operator's time and money. They acknowledge that real-world failure is inevitably going to happen, so they engineer the repair process to be as painless as possible.
It is a remarkably pragmatic approach to design. You don't build a complex machine pretending it will never fail.
Yeah.
You build it knowing that it will eventually break, and you design the underlying architecture to isolate that failure.
Right.
You just swap out the damaged module, leaving the healthy, massive frame of the machine completely untouched.
So to summarize the journey we've been on today, manufacturing engineers looked at an incredibly chaotic, violent, high-heat environment and systematically tamed it. By establishing a common datum for flawless geometry, utilizing peripheral support to bleed off massive physical impacts, employing symmetrical design and independent cooling to defeat thermal expansion, and leveraging modularity to survive factory floor economics.
It really is quite a list.
It is. The sleeve-type spindle basically creates a perfect oasis of stability in the middle of a storm.
And connecting this engineering philosophy to the bigger picture leaves us with a really interesting concept to think about. The spindle achieves its resilience by isolating its most delicate, critical operations inside a highly controlled, modular environment that easily interfaces with a much larger, chaotic system.
Right, a unified reference point combined with modular isolation.
Exactly. So consider how we design the technology in our daily lives. Take consumer electronics, like smartphones, laptops, or even modern electric vehicles. The current trend is highly integrated design. Gluing batteries directly to motherboards or molding components together just to save a single millimeter of space.
Oh, yeah, it's so frustrating.
When one tiny component fails, the entire device becomes electronic waste or requires a factory-level teardown just to fix it. But imagine if we took the physical engineering concept of the sleeve spindle, a unified, stable frame combined with easily swappable, perfectly isolated modules, and applied it to our everyday consumer tech.
That completely changes how I view industrial design. I mean, if consumer products embraced that kind of modular isolation, where a screen or a battery could just be slid out and replaced like a cartridge, we might actually see that same 60% reduction in downtime and waste when our own devices inevitably break.
It's definitely something to think about.
It brings us back to our opening thought, really. True precision isn't just a watchmaker operating in a silent room. True precision is building a system so resilient, so modular, and so intelligently designed that it can maintain its perfect center no matter how violent the world around it gets. Thanks for joining us on this deep dive.